right, it's time to start our colloquium. It's our great pleasure to welcome Professor Elaine Lee from the University of Texas at Austin, this school up the road or down the road. And well, Elaine has been, well, she got her PhD from the University of Michigan, and then she worked for several years at GILA, which is the famous Center for Ultra-Fast Science in Boulder. And since 2007, she became a professor. She has been a professor at UT. And Elaine does some exciting research with novel materials, studying them with ultra-fast lasers. And the topic of her today's talk is novel two-dimensional materials, and they are not only exciting for quantum information applications, as everyone is saying nowadays, one of the hottest things, but you can also create from them a controllable quantum many-body system. So you can just let it evolve and show quantum dynamics that you would not be able to study otherwise. And this is something really exciting, a sort of quantum simulation that makes many people excited about it. All right, without further ado.
Actually, over the past 14, 15 years I've been at UT, I've came here 3 to 4 times. I lose track of a little bit whether this is my 4th trip here or not. So I also like to invite you to ask me questions during my talk. It's not fun to talk to myself, so feel free to interrupt me anytime. I understand this is a colloquium, so I'll start with some simple introduction material. But I like to make a pitch that these semiconductor Moiré supercells is a new platform for quantum information science. You might think, you're just saying this because you think you can get funding to do quantum information science. In fact, actually, I started my graduate career working on quantum information science. We demonstrated the first solid state quantum gates using optically driven semiconductor. And I stopped working on that problem, partially because the material platform we were working on was not scalable at the time. So I was really looking for a scalable system. I think we might have a system that is scalable now. But of course, anything related to quantum control, quantum information and computing are very challenging. So I'm just trying to lay the groundwork and hopefully convince you there's some promise in this material for such applications. Okay, so trying to see how. Okay, so let me do the most important thing first and just acknowledge the people who did this hard work. And I seem to have run a huge group, but in fact, half of them are undergraduate students who patiently help us to prepare these materials and characterize these materials. And people here are the critical players who did the work that I'm going to introduce to you today. And some of them are graduate students and they already moved on to better and greater things, and others are postdocs, and these two are theory from our theory collaborators group, and these two gentlemen have already started their own independent research careers. So we benefit from many collaboration over the years, and the ones that highlighted are the most critical ones for the work I'm going to tell you today. All right. So before we talk about quantum information, let's reflect how quantum physics is important for information technology that we use today, right? So we are storing information in small magnetic domains. Nobody can explain magnetism yet, really, but you really need quantum physics to understand magnetic materials. And of course, spin is an important element to that. And when we process information, we use transistors. And we all know the transistor has already gone down to 7 nanometer channel length. And there are blueprint to chart it out to go to 5 nanometer, 3 nanometer. But you think about 3 nanometer, how many atoms are between the channels, then you realize you're really very deep into the quantum regime. So how do you keep advancing the information processing technology is, of course, a huge challenge. Everybody knows the Moore's law that predict the doubling of the transistor density has already saturated. So we really need to look for very drastic different solutions. Information transfer today are largely classical. We're using a lot of the information transfer rely on light, confined in fibers. Actually, not through satellite, will be inefficient to do that. But of course, already are talking about quantum communication through single photons. There are commercial systems that are being sold that you can do voting through a single photon. Talk about voting securities. It doesn't get more secure by voting through single photons. Something that we as a state care a lot about, obviously. So, and then, so in the looking into the future as a physicist, we don't work on technology that's going to be on the market next year. We ask more fundamental questions. How do we take the next quantum leap and use smaller bits of material? How to manipulate them faster in a way that's energy saving? So these are the fundamental questions myself and others in the field are asking. What are the smallest objects can we use to store information? And how do we use single photons for communication? And what's the limit? How fast we can control the state of a spin or electron to realize information processing? So to answer such questions, you actually have to define how small is small, how fast is fast. I won't be able to get to the point of how fast is fast, but just to say to manipulate small entities in the ultra fast limit, quantum dephasing plays the fundamental limit to that problem. So that's a problem that we also study, but that won't be the focus of my talk. So let's talk about how small is small. So the strategy of controlling material property using quantum engineering is old, decades old. So you start with the bulk material, and your goal is to somehow squeeze the electron motion to either two-dimensional plane or nanowire, or confine them in all three dimensions and make a quantum dot. So you get, all of them would have a role to play in information technology. And in fact, many of the high-speed transistors are already made of quantum well. We're already using these quantum engineered material routinely. As you learn in solid-state physics, once you are confining the electron motions, squeezing the electron wave function, that's small enough when the quantum mechanics really need to be taken into account. You're shaping the band structure, you're changing what energy electrons are allowed to occupy. When you do that, you're really changing the density states, the color of light can emit, and also the statistics of the emitted photon. So this is what we like to call quantum material, that meaning that some dimension of the material is small enough, you're really fundamentally changing the electron wave functions. Obviously, taking a big rubber ball, make it smaller, does not achieve that. But one of the pictures that everybody like to see is done in chemistry and chemical engineering department routinely. These rainbow color are simply semiconductor droplet with the size from 6 nanometer to 4 nanometer. With that size range, you're tuning the color from red to blue continuously. This is because you managed to squeeze the electron wave functions. So this is this will be the routine that we're talking about. Okay, so many of you probably have heard about van der Waals material and started with these two gentlemen. Geim famously was known not to be a greatest experimentalist. He apparently break things in the lab all the time. His graduate advisor told him he's never gonna accomplish anything. And here he is, right? And then they also have a interesting tradition. Every Friday, nobody's allowed to do anything serious. And one of the things that got him most famous at the beginning is he was floating frogs in the lab, right? He's trying to put something in a magnetic field and see what it can float. Apparently, you can float many things, but one of these days they were playing with Scotch tapes, and they realized you can actually create very thin material down to the thickness of a unit cell thickness, right? And that eventually got him the Nobel Prize only 5 years after their initial paper was published, right? This is a pretty, this is a record speed. We recently had a Nobel laureate in Austin, Professor John Goodenough, for inventing lithium battery. He's the known oldest Nobel laureate. He's 97 when he got the Nobel Prize. He's still working full time. So some people are amazing. Anyway, so what they have done is to show actually a large array of material with very different property can be created with Scotch tape. So we have many Scotch tape in the lab. And these are superconductors. There's graphite and graphene. These are very complex oxide material that are also can be superconductor. What I'm going to talk about today is mostly semiconductor. these rather simple compounds that we call transition metal dicogenite. And they're all presented in this early paper. So as far as 2D material is concerned, this is the ultimate thickness you can go. You cannot go thinner than a unit cell thickness. Okay, so this is the material I'll be talking about for the rest of my talk. So transition metal dicogenite, there are 3 layers of atom in a single unit cell. Transition metal in the middle, and then chalcogenide atom on both sides. Now, if you look at these materials from top down, you have a honeycomb lattice. In graphene, you also have what's called an AB lattice, but you have the same atom occupying the AB lattice, that's carbon. This material is just slightly more complicated. You have different atoms on the AB lattice. So these are pretty old pictures. These are flakes grown by chemical vapor deposition. People can grow wafer size now. They're still concerned with the defect density in this material. For the most part, physicists like myself use exfoliation. We buy or get bulk crystals and then take Scotch tape and thin them down. So what do you mean by chemistry? Right. So these materials within a single layer, they're covalent bonded, but between the layer, every 3 atom thickness is 1 layer, but between the layer, they have van der Waals bonding. So in fact, to give people due credit, the MOS2 monolayer was isolated long ago, not start with the Nobel laureates, in fact, right? And published in a decent journal. But what got people's interest, especially those who study optical property like myself, is this paper published about 10 years ago. I should cite another one. I wasn't being complete here. But here's a spectrum, optical spectrum. This is a photoluminescence spectrum. And as you can see, when I look at the 2 layer, which is the green versus the red, the luminescence efficiency grow almost a factor of 100. And that is because there's a band structure change from indirect material to a direct gap material. So that's responsible for this huge enhancement in the light emission. And this peak is due to what's called the exciton resonance. So I'll show you what it is. This is the simplest picture for exciton. So semiconductor has full valence band, empty conduction band. Now you shine some light with sufficient energy, you promote electron from valence band to the conduction band. The electron and the hole left behind actually still are attracted to each other due to the Coulomb force. And this bound pair of electron hole pair is called the exciton. And if you have a direct gap transition, if you have a direct gap semiconductor, it only means the bottom of the conduction band, the top of the valence band are aligned, where they share the same momentum. So photon carry very small momentum when you compare to the Brillouin zone, which is when you describe the band structure of a material, you need to consider the Brillouin zone. The Brillouin zone has a size pi over A being the lattice constant. But if you think about the momentum of photon, you have something that's, wave vector of photon that's 1 over 500 nanometer, for example. So photon carry momentum that's very small compared to the entire Brillouin zone. As a result, any optical interaction, either absorption or emission, is what we call vertical transition. So there's no change in the momentum in the Brillouin zone. So when you have a direct gap semiconductor, it just absorbs light and emit light with much greater efficiency than you have an indirect gap transition, where the bottom of the conduction band and top of the valence band are not aligned. So there's a momentum mismatch, typically relying on photon to participate, to compensate for that momentum mismatch. Therefore, although the van der Waals was very weak, it was sufficient to change the band structure from an indirect gap to a direct gap. So go down to monolayer, you see a dramatic increase in light emission efficiency. I see there's some chat question in the chat box. I'm going to check that quickly. Oh, okay. All right. So, so these are the electron hole pairs is really the fundamental excitation in the semiconductor that's responsible for optical properties. And now this is a more a more formal band structure calculation. Xiaofeng here does these calculations. To me, they're like spaghettis, right? They're kind of messy, but you only need to pay attention to the bottom conduction band, the top of the valence band. And this is the lowest conduction band state, top valence band state. They are not aligned in the bulk. And the states at what's called the gamma point. Gamma point is actually the center of the Brillouin zone, where most of the, this is the center of the Brillouin zone. K is the edge of the Brillouin zone. As you can see, this is a bulk, 4-layer, 2-layer, monolayer. Only in the monolayer limit, the bottom of the conduction band, the top of the valence band now align, become a direct gap semiconductor. Even in the bilayer, you know, this the bottom of the conduction band being here in the middle of the Brillouin zone, and the valence band, the center of the Brillouin zone, they do not align. That make the optical absorption or emission inefficient. So this transition is very critical for the high emission property. And then another thing that's unique is these excitons that we see in the light emission spectrum. They actually happen at the corner of the Brillouin zone. And there are actually two copies, and we call K and a K prime valley. So at the K valley, you know, the color scheme here represents spin state. And photon carry angular momentum of 1. So you actually need certain spin state in the valence band and conduction band to make a allowed optical transition. So it turns out in one valley, you can make that allowed optical transition with circular plus light. And in the other valley, you have to access it using an opposite helicity photon. So valley is nothing new, because if you look at band structure, anytime I have a maximal or minimal in the band structure, it's a valley. Okay, so valley is everywhere. But typically valley does not respond to any control in a specific way. And apply an electrical field or apply a magnetic field, they don't couple to a particular valley in a selective way. But in this material, because the unique spin selection rule, you can actually access one valley using sigma plus photon, using access the other valley using sigma minus photon. Now you have a way to address the valley. Anytime you have a binary degrees of freedom, people start to imagine, can I use it to carry information? So there has been proposal to use this valley degrees of freedom to carry information. And then we also invented a name and called it a valleytronic. Okay. Doesn't make it more useful, but anyway, so this is when you read literature, that's what people mean. In this particular material, you just have this a binary degrees of freedom. You can actually access and control using light. For any 2-level system, you can write a 2x2 matrix, use a block vector to represent its evolution in time. So this is, you know, basically one valley to the other valley can be used to represent 0 and 1 in information. Okay. So the hypothesis early on is that the valley is pretty robust, because electron in one valley to flip to the other valley, there's a huge space to hop over in momentum space, and also spin has to flip, right? So now we know, especially optically controlled valley degrees of freedom isn't so robust. But that's a detail for the purpose of my talk. So let me also expand the quasi-particle that's relevant to optical property. So I talked about electron hole pair, which is exciton. And because the material is so thin, the Coulomb field that bounds the electron hole pair actually permeate outside the material, make the binding energy very strong, a few hundred MeV. You know, the typical band gap for a lot of material we're familiar with is on the order of 1.5 eV. So a few hundred MeV is very significant. And you can have additional quasi-particle called trion, which is an electron hole pair together with another electron, or 2 electron hole pair bonded together that we call biexciton. And all of these species has been studied before for quantum information science. If you can study one exciton at a time, they will actually act like single photon emitters. And for this material, they have huge dipoles, meaning the dipole is just a quantity, R dot E. You take the, you integrate over the wave function. It gives you a quantity to characterize how strongly this entity coupled to light. So large dipole means they couple to light very strongly. For thin layer, single layer material, if you shine light resonant with the exciton, they absorb almost 10% of the light. So that strong absorption also dictate whenever you create an exciton, it tends to recombine very fast. How fast? This is the how fast is fast in my talk early on, about 200 femtoseconds. So for those of you who don't do ultra fast science, what is a femtosecond? So one femtosecond is 10 to the minus 15 seconds. And give you an example of ratio in time. If you think about dinosaur age, 65 million years ago, divided by what we call fast in a heartbeat, a second, right? Dinosaur age over a second is a second over a femtosecond. In terms of ratio of distance, if you think about less than a millimeter and compare that to the distance between sun and the earth, that's the same ratio. Sun and earth distance divided by the millimeter is a second over a femtosecond. So, so certainly it happens very fast. And we can actually track this using ultra fast laser. But again, we're gonna stay away from that. And just say, because the binding energy is so large, it makes these entities very relevant for devices, even at room temperature. So this is the hope that you can actually use these entities to be single photon emitters or entangled photon pairs, where a trion, because when the electron hole recombine, it still leaves a charge behind, and there's a spin associated with that charge. So trion can be used as a way to entangle spin and photon. Another way to say it, I can write the information in spin, let it carry it away by a photon. So you can project information on a spin to a photon. So this is a useful way to do what's called the information transduction. Put information in one degree of freedom, leave it to the other entity. So building on this early work in the traditional semiconductor, take advantage that these entities are all stable at room temperature. We want to speculate how they can be useful for quantum information science. So this is what I'm going to do in the next 20-some minutes. But before, there's also more complicated excitation I'm going to skip for today's talk. But before I go on, are there any questions so far? I was hoping to avoid talking about it, but yeah. So the question is, I have illustrated both attractive polaron and the repulsive polaron. When do they occur, right? So in fact, they both exist, but one attractive polaron has lower energy than repulsive polaron. We're learning they have very different quantum dynamics. So, but we're not there yet. But as you can imagine, it can be a way to address a number of electrons using a single optical excitation, right? So from that perspective, it's probably useful. But yeah, optically, they both show up as a resonance. But, basically, this is like electron hole pair are actually attracting the electron close to them. This is what this is the original position. They're attracting the electron close to the electron hole pair. In the other case, they're pushing the electrons away. So the attractive polarons are more energetically stable. Probably that's why you're more comfortable with them. But the repulsive polaron can be observed if you dope the material properly. So they exist. Okay, but I have not even started introducing the main entity in my title yet. So I want to make what I mean by a Moiré superlattice. I've been talking about monolayer, But now let me take 2 layers and vertically stack them, okay? So now imagine you have 2 identical layers, and if you manage to stack them perfectly, then you just have a bilayer, okay? So it's natural. But if when you literally do this in a lab, it's impossible not to have any small rotational angle. But when you have that, you can see there's a superstructure that's developed, and that's an in-plane energy confinement. I can change the size of that in-plane energy confinement or the in-plane superlattice by simply increasing the twist angle. So I can prove that to you. We're all scientists. We have to prove things to you. This is an outline for the next half an hour of my talk. I'll skip to a description. I'll talk about how do we measure the Moiré potential, Moiré superlattice. And then once you introduce that periodic modulation, you make the excitons and selection rule far more complicated. We're going to show you how you can change the twist, the resonance lifetime and how they move, all just by changing the twist angle. And then I'm going to show you things are not as simple as I've made them sound so far. But let me show you this picture that's done by what's called the scanning tunneling microscopy, that take a sharp metal tip, start injecting electron into the material. The tip can be so sharp you can see individual atoms. So, but let's look at the picture. This is a picture taken by TEM, transition electron microscope. These dots are literally heavy atoms in those layers. And this material are 2 bilayers, but they don't share the same chalcogenate atom. As a result, their lattice constant differ by about 4%. So this material is actually grown using chemical vapor deposition by smart chemists, which I don't know how to do. When you grow them, they tend to align on the crystal axis because that minimizes the energy. So now, because the lattice constant is different, you still have a superlattice, because maybe at what I call the AA point, the top hexagonal is perfectly aligned with the bottom hexagonal, but because lattice constant is different, I move away by tenths of a unit cell. Now a different atom in the bottom layer start to stick out in the top layer, the center of the top layer. So I can have these high symmetry point that I call AA, AB selenium, AB tungsten. They are represented by the top, second, and bottom. The atomic alignment at these 3 points still maintain threefold symmetry, meaning I can rotate it by 120 degrees. It would just fold back on itself. And many other regions is what we call the bridge region. You don't have a perfect threefold symmetry. Not only because the semiconductor energy level is determined by orbital hybridization, because the top and layer atoms are aligned differently as you shift around the Moiré supercell, the band structures are different as you move from one point to the next point in the Moiré supercell. So this picture is a topology picture, which shows you the spacing between the layer actually change periodically. But it can also be viewed, I can also build a picture that represents the electron local density. So actually these bright points are the point where electrons tend to naturally puddle. Okay. So I already created a canvas of material where I define locations where electron would like to sit preferentially. And this is scalable. I can build many of these sites by simply make the layer bigger. This is measurement. So this is the measured band gap at several high symmetry points. As you can see, the band gap locally changes more than 200 MeV. So I have this periodic checkerboard pattern, and there are preferred energy traps where electrons or holes or excitons would like to sit. So that makes them a really interesting quantum material that define individual quantum systems, single electron, single hole, or single electron hole pair, and put them in a predefined position. So this is what make them really attractive. Okay, again, I'd like to pause and see if there are questions from the audience. So here, the chemists, they just start growing them in a vapor form. They heat up some powder, and they would just energetically find this structure that's energetically favorable. But I don't know how to do that. We literally take material and we stack them. We can rotate them. We can rotate them because the van der Waals force is very weak. Now I can even just simply control the size of the quantum box by twist the angle. That's what we do. But this is what nature does, because the atoms will be allowed to settle down at minimal energy states. They can still form this very well-defined checkerboard of Moiré superlattice. So we know the concept of superlattice before. We grow very thin layers and we build the one-dimensional superlattice. Now this gives you a way to construct an in-plane superlattice with many easy controls. And the beautiful thing is there are many van der Waals materials. Some are magnetic, some are ferroelectric, some are semiconductor, others are insulator, others are semi-metal. You can stack arbitrary combination of them on top of each other because you do not have to satisfy lattice matching condition. You just have a gigantic libraries to build your heterostructure with. And then we rely on theorists to tell us what are the most interesting combinations to put together. Otherwise, we can never exhaust them in the laboratory. Okay, please. Yes. So the question is, this is periodic in 2D. What about the third dimension? The third dimension was already confined because I use a atomically thin layer. The electron is not going to be able to jump out of the material. That they have to overcome work function that are on the order of 5 to 6 eV. Putting more stack, feel free to do that. Okay, so it's very exhausting to do it, but certainly that's the direction that people are going to. I just need 2 layers for now. Okay. Already I built this checkerboard or quantum box. You know, we talk about second quantum evolution, like second quantum revolution. It's all about starting to get better control of individual quantum systems, right? So we know quantum mechanics is everywhere. We cannot explain anything about solid without quantum mechanics. What are the challenges really? Controlling individual ions, controlling individual atoms. Now we constructed a solid state platform where we can actually set the stage for electron or holes or these electron hole pair to occupy. Like an optical lattice, except for it's now in the real material, with an intermediate length scale of few nanometer. It's 10 times bigger than the atomic scale, but also 10 times smaller than the optical lattice. Okay. Other questions? Okay. So this is how I view optical property behave as well. I can have this bright spot. They're just emitting light. And if I do it right, they will emit light, photon one at a time. Nobody has proven that yet. Because the supercell, the unit cell is very small, on the order of 10 nanometer. As you know, when we do optics, we focus light on the material. We typically cannot get better than a few hundred nanometers. And so this is a challenge for us to understand how the supercell with a 10 nanometer spacing control optical properties. Okay, so now I come back to electron hole pair or bound electron hole pair excitons. I'm going to change a material combination on you now. So I'm going to use a MoSe2, tungsten Se2. They share the same chalcogenate atom. The lattice constant is very similar. Now the only thing that determines the unit cell is the twist angle between them. So when I put them together, you actually always have to ask how the bands, conduction band in one material and the valence band in the other material, how do they line up? Turns out in these material, typically they have what's called a type 2 band alignment. meaning the minimum of the conduction band sits in one layer, the maximum of the valence band sits in the other layer. Okay, so my students, my undergraduate said, you just understand the hole as if they were the bubbles in your drink, in your Coca-Cola, and then the holes just flow to the top, electrons sink to the bottom of this layer. So if I electron in one layer, hole in the other layer, you set up a different kind of exciton that we call electron hole interlayer exciton, where electron and hole are in different layers. So these excitons have very different property compared to the intralayer exciton. They absorb less, they live longer, and I'm going to show you how we control their energy and dynamics using the twist control. Another thing that happens is that we're going to come back to these three high symmetry points. I want to discuss selection rule again. So now remember, I said there's a K valley and K prime valley in monolayer. That concept is still valid in the heterostructure. But it's much more complicated if I only look at transition in one valley. I now have three different sites, A, B, C site. If I can put electron hole pair in one location, they would have different selection rule. In one location, they will have sigma plus. In a different location, they will have sigma minus. In the third location, they actually have a dipole that's perpendicular to the 2D plane that does not couple to plane wave that shine on the 2D material easily. This is just one valley. I still have the time reversal copy in the other valley, meaning that whenever I have a real space exciton here, I have a sigma plus transition in K valley. I also have a sigma minus transition in K prime valley. So it's a mess. Okay, so I have many transitions that's possible. So to summarize that, when I create a Moiré superlattice, I have this energy modulation, but now I also have this optical selection rule modulation in real space. If I can actually harvest this, I already created a regular checkerboard of emitter that even high chirality coded in their property. So I just provide this very rich material system to you that can have interesting quantum emitter properties. They're positioned regularly, and they have interesting variations of energy and the chirality. So again, I want to pause and see if you have any questions to clarify. Yes, please. Yeah. Right. So that, the question is, if I can put electron in one layer, holding the other layer, can I allow them to separate far away from each other? So you do have this Moiré potential that tend to there's a real space variation of the bands. So there are preferred positions for electron holes. It's actually, we don't know actually exactly where the electron hole sits in real space. It's not easy to probe. But typically people are assuming what's called the Bohr radius, basically the separation between electron holes still remain to be about a nanometer, 1 or 2 nanometers. So you can have situation that, maybe electron in the one part of the Moiré, hole sits in the other part of the Moiré. There's still probably sufficient Coulomb interaction left to give you a bound state. Okay, so that's possible, except for we lack the tool to find them, precisely right now. Other questions? Yeah. Right. Yeah. Right. You want me to compare the intra and inter? There are many differences between them. Besides the dielectric constant, you referred to, the dipole moment is already hugely different. So, the intralayer exciton is about factor 20 smaller than the other. So, I think that Moiré, I showed the one way of creating a Moiré superlattice, which is the energy band modulation. You actually can have structure that have minimal energy modulation, but the dielectric constant variation is another way to create a Moiré superlattice. So in a certain way, it depends on the structure, right? So they probably still follow this period, but you can certainly, you do need to take into account the dielectric constant variations as the full picture for the Moiré potential. So I didn't articulate, there's a lot of details. The potential trap for electrons is actually different from for hole. It's yet different from exciton, right? So they're all very different. There are many details to be worked on. Okay, I think you have a question. Okay. Other questions? Okay. So now we've been making this for the last 4 to 5 years. And, so when you stack them together, you do get these interlayer excitons that appear in lower energy. They appear in lower energy mainly based on the band light. But then at the beginning, everybody was making Moiré, vertical structures with probably pretty poor quality. Meaning there's a lot of variations of the local strains and defects. So starting a few years ago, people start to encapsulate them with this atomically flat HBN insulator. It really played a major role to improve quality of the Moiré superlattice. It's just more painful for students to create. Now instead of 2 layers, you need 4 layers. Okay, that's not even sophisticated enough. Hexagonal boron nitride. They're different phases. The cubic boron nitride, hexagonal boron nitride. Interestingly, for people interested in material science, everybody get these crystals from a Japanese group. To perfect the growth, they grown 900 times. So if you're frustrated as a graduate student, your experiment is not working, just know it doesn't work at the beginning for everybody. But these groups are now the sole supplier for all groups around the world that are working with these materials. So when you encapsulate them, the uniformity of the Moiré superlattice gets better. We start to see fine structures underneath this broad resonances. And we didn't know how to interpret them until my hardworking students made a dozen of them. We start to see, trends. So this is a Moiré superlattice with 1 degree. This is a Moiré superlattice with 2 degrees. We're only looking at the interlayer exciton right now. Okay, so these are low energy transitions, interlayer exciton. We measure them at many different points on the sample. As you can see, there's still some fluctuations. There's still some bubbles and wrinkles. But you start to see with a 2 degree sample, the energy spacing appeared to be larger. So if you allow me to use the simplest quantum box model, you make the box smaller, you learn quantum mechanics, you make the energy spacing bigger. It's a very simple picture to explain this spectrum. And very peculiarly, in the 1 degree sample, we use the sigma plus to pump the K value, for example. And then you see the emission have an alternating selection. So that is suggested to us that is related to the Moiré. That's another evidence to suggest this is related to Moiré energy modulation. So I would say this paper published 2 years ago was published together with 3 other articles, all try to articulate or try to explore how optical spectrons are changed by the Moiré potential. We're still arguing a lot about how to interpret this spectrons. There's still a lot of controversy and conflicting results, different ways to interpret the spectrum in the literature. Okay. So I expect that debate to go on for at least another 3 to 5 years. Okay. So this is another lesson for the students. Not every paper written in the best journals are reliable. So ideally, you want the better spatial resolution that you can probe individual Moiré supercell. Right now, we're using a micron beam. We're actually hundreds of a thousand or a thousand Moiré supercell at the same time, right? So we don't know what a spatial inhomogeneity that are present. You know, for example, this peak are kind of broad, but why is it so broad? Perhaps just because of small variation in the Moiré cell. And frankly, ideally, if I have the choice, I want to work with chemically grown samples. I've shown you the STM image. It was actually pretty uniform. Why did I still torture my student, ask them to stack them? It's because the CVD grown sample has a lot of point defects that make the transitions very broad. Then they just kind of merge each other. I don't see this discrete state anymore. So that's why at the moment, we're stuck with the mechanical stacking method. If our friends in chemistry figure out how to reduce the defect level, they give us more uniform Moiré superlattice, right, with sharper peak, that'll make our life so much easier. Yes, please. Good question. This is about 20 Kelvin. So we're not going to the extreme of 100 millikelvin yet. But also this transition is stable at room temperature. They will survive at room temperature, except for the line width will get broader because of interaction with photon. Then again, we lost track of this discrete resonance. Sharper, yes, I love to. It only take $1 million to buy a diffusion, dilution fridge, right? So I know that you guys pay someone $1 million to build a dilution fridge, but then we need to bring light into that dilution fridge as well. So, and people don't like you to touch their dilution fridge. It's $1 million machine. I've been trying to convince someone to let me put some material into their fridge to lower the temperature, further narrow the line. I haven't succeeded. Okay, other questions? All right, so just to throw in another possible interpretation, maybe the excitons are not sitting at different locations of the Moiré supercell. Instead, there's a global energy minimal, but because the energy trap is sufficiently deep, I can actually have ground state, excited state of the exciton state. And these are calculated center mass wave function. And these are calculated absorption spectrum that says, even if they're localized in the global minimal in the Moiré potential, I can confine more than one state. They will also have this alternating selection. So again, this is something we don't know. We don't have the experimental tool to rule out one explanation versus the other. So our own paper picked this interpretation because some other supporting experiments, temperature dependence, lifetime measurement, but I won't bore you with those details. Just to know, we're just getting started to understand this optical excitation in the Moiré superlattice. So, so now we think, how do we, another way for me to understand, for us to further convince ourselves this has anything to do with the Moiré potential is that let's start tuning them, right? So what we find out is that the lifetime, how long does interlayer exciton live, or whether or not they can move around, depends on the twist angle. So when the twist angle is small, when the Moiré supercell size is large, I tend to localize these carriers. But when I make them the unit cell to be like maybe 2 to 3 nanometer, and then they can actually smooth out the energy landscape and start moving around. So we've also tried to bring comparison samples, this time grown by our friends who know chemistry. When they grow these two materials stacked together, because the lattice constant is so close, the layer each deform a little bit. Actually, in this material, there's no Moiré superlattice because each layer just stretch themselves or compress it a little bit. Energetically, they tend to be perfectly aligned. Now have a comparison between the same material without and with Moiré superlattice. So this is also our way to check, are we insane? Are we just imagining things, or let's do some comparison experiment. So what we found is in the CVD sample, the excitons can indeed move. And in this particular data, they're clipped by the boundary of the layers. So they're not huge, they're a few nanometer, few microns. So these spectrons, I should explain, this is a spatial extension This is energy. So this is CVD. So I just have a broad blob of interlayer exciton. And this is a stack sample. I actually have multiple transition I can distinguish. The spatial extent, exciton move in the CVD because there's no Moiré potential. But when I have a small twist angle, they're localized. The spatial extent, still a couple micron. That's because I cannot focus my optics better than that. So this is actually a diffraction limited experiment. So we cannot tell exciton is moving. We have not proved they're perfectly localized in the individual cell because we don't have that spatial resolution. But we can say they do not move beyond the micron size we can see. And then we can also compare two samples with 1 degree versus 3 degree. With very low excitation density, the excitons are moving with a 3 degree sample. Because the unit cell, the Moiré supercell is smaller, they now can hop around. Another reason is that they live longer. So it's really, I only want you to see the bottom plot. So these are 3 samples, 1 degree, 2 degree, 3 degree, 3.5 degree. This is the lifetime of the exciton. As you can see, the lifetime actually changes by more than an order of magnitude when I simply change the twist angle. So partially is because the same argument I've been saying, whether it's a direct transition in the momentum space or it's an indirect transition in momentum space. When I twist these layers in the real space, I'm actually shifting the bands in the momentum space as well. So this picture would hold in the momentum space. I'm shifting the top of the valence band from the bottom of the conduction band in this bilayer by a small amount, but that's sufficient to change the lifetime by a lot. Okay, so this is one of the mechanisms. The Moiré superlattice actually kind of relaxed the momentum conservation requirement. If I only consider the band shifting, I will be looking at a lifetime change by 3 orders of magnitude. But now with the Moiré superlattice, they're only changing 1 order of magnitude. So, but again, so this have a profound change on the dynamics. That's related to the diffusion LC. So I see I've essentially run out of time. The last thing I want to show you is everybody's seen this picture. I've talked to other faculty members. They have this in their talks, but they're not Legos, right? They're not rigid. They're really difficult to manage. And the lattice changes. And we now realize with bilayers, they actually form this triangular potential where within the triangle, you have a perfect atomic alignment. And the different stacking only happen on the boundary of these triangles. So that would potentially completely rewrite the selection rule I was telling you about. So, but this kind of lattice reconstruction mostly happen in what we call the homobilayer, meaning we start with a monolayer and then construct the bilayer using the same material. So I won't elaborate on that because I do want to speculate what else can we do with in the quantum information science? So one thing is single photon emitters. So there are a lot of solid state single photon emitters, but they're mostly based on defect in a high gap material or these self-assembled quantum dot. As you can see, this is a quantum dot. Here's a quantum dot. They're randomly spaced with changing size. You can also modify a carbon nanotube, but none of them has well-defined directions and they have different energies. But with Moiré supercell, I potentially have a regular array, a range single photon emitter. That's one area that it can make an impact. And then you can use it for what's called the basically spin photon transduction. At the time this review article was written 3 years ago, Moiré superlattice was not even in people's vocabulary at that time. So now within 3 years, we've come a long way to understand how they can be used in quantum information science. And then you can actually do quantum simulator. Condensed matter physicists all learn about these, Hubbard model, K-Malin model. Sometimes they refer to, for example, Hubbard model refers to, this regular array of spins. We actually don't know whether the spin will be aligned or anti-aligned. It's not analytically solvable for decades. Now we have an opportunity to create a real spin, checkerboard of spin. We can ask how they're aligned. So this is why many people have been proposing this material as what's called the quantum simulator. So you construct a better defined and better controlled quantum system, simulate problems like ferromagnetic order, antiferromagnetic order that we do not know how to solve. So this is why they're useful there. And there's some initial evidence that has emerged last year, but I would say these results are all going to be debated in the next 5 years, if not longer. That really, and then a lot of people have speculated the large array of problems you can simulate in the Moiré superlattice. So I've talked about very limitedly Moiré excitons today, but you can simulate a quantum magnet, meaning by simply changing the twist angle, you can create an antiferromagnetic material or ferromagnetic material. You can simulate, we know they're superconducting. They can be superconducting or insulator simply by changing the twist angle. So this is really a physicist's dream. That if I talk to a chemist, one of my friends in chemistry department, he said, physicists are so wimpy. They don't want to work with new materials. You give them more than 2 atoms, they're like too much. We love graphene because they only have carbon atoms, and we can already create a correlated insulator and magnetism. We can create everything out of just 2 sheets of carbon atom, right? I think they have, that they have their point, but we just really want to start with the simplest material and realize as rich phases of matter as possible. So that reminds me that things for a very long time, we can only look to our AMO colleagues. They are having so much fun with, trapped ions or Ripper atom simulators. Maybe we can reclaim some of that back to solid state systems. And so we now have a checkerboard array of quantum system too. Let's do some quantum simulation. Right. So with that, I'm finished with my talk. I'd be happy to answer more questions, please. Okay, all right. Thank you very much. I appreciate it.
Oh no, she used.
Yeah, because there are people on Zoom, right? They wouldn't know what I'm pointing here. Right. I think you want us to, the question is, can I, yes, there are theorists already proposing that. And they say, let's take a optical lattice. Let's make 2 optical lattice, rotate them. And you talk to the experimentalists, they're like, get out of here. So it's too hard, right? And certainly people are speculating that, again, the benefit of cold atom is that, you can address the individual unit cell, right? Because they're on the order of 500 nanometer, they have that addressability. In principle, it exists in the solid state Moiré superlattice because you have tools like STM, right? You can, address individual spins. You have tools like near field optical microscope. In principle, the capability is there, except for it's still a nightmare for anybody who try to do it realistically. I think, yeah, they have already imaged it, right? So, the STM picture is exactly that. They're probing individual cells and ask, what is the local band gap? What is the local, if you have a spin result, STM, you can ask, what is the local spin orientation? I think that's going to be answered, in the next. Not yet. I gave sample to Marcus, and that's why, yeah, so that's why you should help me to hassle him. He promised to do that, but Yeah, certainly. I think we're right. So the question is, can I use any super resolution technique to optically to address individual cells? The answer is we're really at the hairy edge. I didn't show some of the image. If you have homo bilayer, you can actually construct Moiré cells that are 100 nanometer. So it is possible to address them individually, right? STEM may not be the best answer because, as I understood, the STEM rely on nonlinear optical, you're saturating part of the beams, right? So you still have light falling on other unit cells. It's really tantalizingly close. You should be able to address it. There's what's called a light shield technique. Basically people are already creating these super resolution array of optical beam. If you can overlay them with the Moiré, you can potentially do that. Yeah, so I think it's with enough determination, I think it can be done. So typically around 1.5 nanometer. Sorry, 1.5 EV, sorry, energy. 500 nanometer, 600 nanometer, all of these mostly have emission anywhere between 600 nanometer to about 850. Actually very conveniently located in the range of the laser we all have, right? Tesla the laser can really address it. Hundreds giga. Milli EV. So 0.2 EV, not the, maybe you're a high energy physicist. Yeah. Right.